In this lecture, we will look at entropy changes in an ideal gas. So in a series of lectures starting from the previous lecture, we are going to compute entropy changes in a variety of systems. The general strategy is this. You want to go beyond this expression. Okay, so this expression is sort of limited because such processes are not often seen in reality. So we derived some expressions called the TDS relationship, and then the central emphasis is to develop a computational procedure that doesn't depend upon processes but depends upon changes in state properties. Okay, so there are two TDS relationship, one for a closed system, another for a flow system. So this was the emphasis, and in the previous lecture we implemented this for solids and liquids because the specific volume changes is marginal. We can neglect that. So that gave rise to certain simplifications. So we look at another class of model systems, which are ideal gases, which provides a range of analytical expression so that you can get the essence of the computation, even though the ideal gas approximation may not be valid for many systems that you see in practice. In the previous lecture, just as one specific case, we also looked at isoentropic changes, and just a simple analysis tells you that isoentropic changes will also be isothermal. So when you move on to ideal gases, so we have this expression. In addition to this expression, general expression, we can substitute the ideal gas law into this expression, which helps us arrive at this expression. So here, for most of the systems, specific heat capacity is a function of temperature. We'll see how we are going to handle that. So this is using the first TDS relationship. Using the second TDS relationship, this is for closed system, this is for a flow system, we can arrive at, in a very similar procedure, we can arrive at this relationship. So there are two ways of moving forward from here. Just within the scope of the class, we can assume that the specific heat capacity doesn't vary that much. So the way to handle that is, that scenario is, if you know the specific heat capacity, for example, you can assume we can come up with an average specific heat capacity and incorporate that into this expression. Or this is, if you have to really do a careful analysis, you can use numerical methods to do this integral and so on. So in a typical engineering system that is implemented, but within the scope of the class, so that you understand the essence of the calculation, this kind of analysis is good enough. So if you have an average specific heat capacity, which is an approximation, we can just integrate and get these expressions for an ideal gas. So there is as isoentropic processes are important in many of the engineering system, we look at it as a special case. So for isoentropic case, this would be 0. So we can rewrite this and get a different expression, just valid for an isoentropic case. So again, this is the expression which you get for an isoentropic case. It's just a simple rearrangement. Because it's an ideal gas system, we can further use the ideal gas relationship to express specific volume in terms of pressures, and with a series of very simple manipulation, we get 3 different expressions for isoentropic analysis of an ideal gas system. So this is often used in, to illustrate what's going on in these systems. So where do we go from here? We look at the next class of system, which is very relevant for engineering system, which is reversible steady flow work. How do we do entropy changes in such a kind of system? That will be the agenda for the next lecture.